Kubernetes drops Docker, what does it mean? Is all we learned so far about containers and container security obsolete? How do they build their containers if they drop Docker? You know what? We will drop Docker too. And at sec4dev, we will not only build our containers, we will also break them. Kubernetes is quite a complex system. It consists of many parts, and those are communicating with each other. But today we will focus on the node, on the computer that's executing the containers. And we will have a look at how we can create our containers by hand. But what do we need? We need an image, of course, because that's the program we want to run. And then we want to isolate this image from our host. We want to restrict access to devices like our hard disk. And then we want to lower our user privileges in order that this container can't affect our own system. Same for network. And then we have to deal with some of the breakouts, right? First, we need our container image. So we take Nginx, our program we want to execute, and this program needs some distribution-specific parts like configuration files or libraries. And we take those from a distribution like Alpine Linux. Usually, this is all configured in the Docker file. So we take Alpine and add our Nginx and copy some configuration files. So let's do this by hand. We create a container folder, and next we want to add our Alpine image. So let's pull that from the distribution point, and then we extract the image into our folder. And after that, we are ready to go because we have in this folder our Alpine container. And now we want to add the Nginx. For this part, we want to configure a name server in order to install something. So we add our 8888 name server to the resolve conf inside the container. And now we can chroot into the container and use the package system in order to install the Nginx. If you do this by Docker, all this is done via the Docker file. So the Docker daemon pulls images, adds some stuff, and all lands inside a folder. But you don't see that. Let's also add a file on the host and inside the container folder. As we go through the steps by hand, we can then see where we are standing at. So the old way to run a program within a restricted environment would be to use cgroup. And we see we can't really get out of our cgroup by just reversing up. But what we can do within the cgroup is to see that we have network access and also we see all the other processes. We just have to mount the proc file system. What we can see here is all the processes on the system. So as we work with containers, we want to treat our program as evil. And we want to protect our system from this program. So we employ kernel features like namespaces and cgroups in order to create walls. Those walls are the building blocks of containers. So let's see how they work in action. First, we have a look at the mount namespace, and a new mount namespace is created initially by the bootstrap process. So init has the first initial mount namespace. As init creates new child processes, this namespace is inherited to all the children. So normally you have a common mount namespace and mount list. You can also see this as you browse the proc file system. For example, init, the process ID number 1 has the same mount namespace as the child, which is in our case the bash. And here you see a number, so something 40 is the initial namespace. So what we like to do is to create a separate namespace, therefore a separate mount list, and manipulate this new mount list. After we created the new mount namespace, we have to switch our new root. So it's not the old file system anymore, it's the container folder. Let's start by creating a new mount namespace. This is done via unshare. And now we have a copy of the old mount list in a separate namespace. So we can now manipulate the mount list in order to prepare our container for the change of the root file system. And this is done via pivot root. The pivot root command takes the old root and moves it to the folder old root and switches the new root into the current folder here. So now we switch to / and we can now see that we are in the newly created file system. So we now can just unmount all the other stuff we don't need anymore. For example, the old root, we can get rid of it. And the last step would be to exec, for example, a shell or the target process. All right, and we can also try to traverse up. Maybe we can access the old file system, but no, we're caught inside the container folder. And we can also try to mount the proc file system in order to see all the mounted file systems. And here we see that we don't see the mounted file systems of the host anymore. But stop! Docker is about Docker files and images. And Docker pulls the images from the registry. Why are we talking about the file system? Indeed, Docker pulls the information from the registry, and those images are basically tar files containing different layers that are optimized for runtime or for development. In the end, those layers are folders in the file system, in the libdocker overlay file system, and those get assembled as you start a container, and then this is the root file system of the container. For example, within a Alpine container in Docker, you see that there is an overlay file system. This file system has different layers, and you see here in var libdocker are the different layers in the host file system. For example, this particular folder contains the main Alpine image. And if we ls that, we see the different folders. And then we see an overlaid folder. And this contains, for example, changes or what we're currently working at. To demonstrate that, we can touch, for example, an XXXX in the container. And in one of the layers, there is the change happening. So for example, on the host, on the node, we see the XXXX file. Okay, image and the file system is done. That's good. What about the device access? Can we access maybe the hard disk within our container? Can we break out of this container? We're still root. So we have high privileges on this within this container, and we can create device nodes. So we can access hardware via the block device SDA1, which is our disk. And this is the disk of the host. So we can try to read from this disk, and indeed we can read the superblock. Let's try to mount it. Indeed, we can mount it. And we see the new file system here. So let's just cgroup into the new mount, and we're out. We're back on the host on the root file system. Neat. One problem here is the shared device. So we need some mechanism to control who is allowed to access a specific device type. And this is done via control groups. In control groups, or cgroups for short, all your resources are represented as a tree. And you can create subgroups to define how much resources are assigned to each process. You can also create a list which process is allowed to access which device type. And this could be exactly what we need. So what we want to get rid of is the access on devices, but in particular block devices. So that's our current process ID. Let's switch to the host. And here we can see in the C group for devices, there is a devices list file. And here we can read the information, what are devices that can be accessed by all the processes. Here we can see then that all the device types can be accessed, read, written, and device nodes can be created. And now we want to change that. So we want to create a new subgroup. We call it myContainer1. And we want to change the denied device types. So we want to restrict block devices. Here we have B, all block devices. And now we can try to add our process, the process ID number 5966, to this particular C group. So now the process ID is added to the device C group. And now it shouldn't be possible to read from the disk anymore. And indeed, even if we're root, we can't really access the device anymore. Let's try to mount the device. Maybe we can mount it. Nope. We're root, but we can't mount the device. Cool. Docker also heavily uses C groups, not only for CPU and for memory usage, but also for device control. For example, if you just do a Docker run, you see that the dev file system is only very loosely populated and only character devices are present. If you have a look at the Docker C groups, you see that in the devices C group, Docker created a subgroup under Docker. And if you switch to the host, you can also see which permissions are set on this particular C group. So let's switch to the devices C group in Docker and read out the devices list. And here you see that only character devices are allowed to read and write and make not, and block devices are heavily restricted. This changes if you do the privileged flag. Then you start a privileged container. Docker populates your dev file system with all the device nodes that are present on the host system. So you can interact with these devices, and also the Z group, the according C group for this particular container is not restricted. So as you use privileged containers, you can break out on the system. But this is also intended because privileged containers are used for system operations. Next up is the drop of our own privileges, our own user permissions. But before that, let's have a look at one escalation technique we can use because we have a high privileged user within the container. We have removed the device control and the device access, but what we see is that the processes share a common file system, the proc pseudo file system. Unfortunately, this is a way to tunnel through the processes file descriptors. Let's see this in action. We are root and we have proc mounted. This is nice because we can retrieve information about the other running processes, like the state and open file descriptors. For each running process, there is a process ID number in the proc file system, and you can browse through that as your root on the system. You can also read the file descriptor list in the proc file system for each and every process as root. Those file descriptors are somehow special. They are represented as symlinks, but indeed you can like tunnel through the proc file system to this particular file or directory. What I'm looking for here is a directory, so a open directory file descriptor, and here it is, number 9, to a data directory, and it's process number 622. So let's copy that, and we will try to access this file descriptor. So it's file descriptor 9. And here we can see that, yes, we can access it. And now it's weird because you can traverse up through that file descriptor. And oh my gosh, here we reach the directory from the host. So as we are root, we can ch root into it. And now this is a breakout to the host through the proc file system. So the problem here is we have too many permissions. But do we really need the root user? Indeed, only for very special permissions, right? It's quite common to run something as root because it has to open a high privileged port. As we run it as normal user, for example, I created the www user, we are not allowed as user ID 100 to open a high privileged port. What we really need is something in between, not root, but not a normal user. Since a long time, the Linux permission model got split into many different parts, and those are guarded by so-called capabilities. For example, to open a high privileged port, you need a special capability, and it's called the capnet bind service. You can review the capabilities in the proc in the self-status file. So the plan is to drop all the capabilities we don't need and to keep only those that are really necessary to run our program. How can we do that? Let's review that again. With root, we have all capabilities represented through this mask. We can also pretty print it with the capsh command, and we see that we have almost all capabilities. As we switch to a normal user, we lose all capabilities. So as we do this again, we are user ID 100, and now as we review the capabilities, we see in an effective set, the checked one is 0, so we have no capabilities. capsh also says current is 0. We have seen there are several capability sets, and the most important one is the effective set, because that one is checked as you issue a command. The other ones get into play as you create a new process, because then you need to have an inheritable set and an ambient set in order to have an effective permission set in the target process. So let's try to set this via capsh. So we want to have our bind service. In order to do that, we have to have the set cap and the set git and uid in the effective set. And only the bind service we inherit and we add it into ambient in order to have it in the target process. The user is www, so as we ran this, we have a process that is run as user and only holds that one capability, that bind net service. So as you run again, for example, netcat to open a port, this works. Docker also does this. As you run an Alpine image, you don't have the cap.sh, but you can review your capabilities in the proc self status. And you can then decode them in your host. So you immediately see there is not 3FFF, the mask, and we see that's only a limited set. If you compare that to a run with an privileged container, you see that Docker gives you automatically all the capabilities that are possible. So you see 3FFF. And again, then you can decode the 3FFF and you see what capabilities are missing in a standard container, even as you run as root. So what's still shared? One is the network namespace. So we share the same network with all the other processes. This means we can port scan the node. Let's see this in action. We can query the open ports with netstat, and we share the same network namespace. So we also see that running services on the node. We can also try to download nmap, for example, a static linked binary, and run it on the node or the other containers. Therefore, we can try to find open network services on the node or other containers. Another problem is that you see all the interfaces. And of course, we don't want that. What we want is another wall, network namespace that only shows us our own interfaces and not the ones of the host or node. The idea is to create a virtual Ethernet cable and to connect it to a central point like a bridge, and then we can attach all the other containers or the host itself if we want to have communication between them. So all those things like the container, our container, a separate container have their own network namespace. And of course the host holds a separate one, a separate network namespace that governs, for example, the bridge that we create and, for example, the host interfaces. We can configure that with the IP command. So we pull our current process ID and then we switch to the host side of things. And here we create a new separate network namespace and we all assign it like numbers. For example, our container has number 42, of course, and we create a new namespace for this container. And then we can attach our process to this network namespace. Now we have to create our Ethernet cable, and it has two parts, the host part and the container part. We switch the container part to the network namespace of the container, and then we configure the IP address space inside the container with the exec command. Same is done with our host device. So we pull up our host device and our container device, and we add a route in order that the host knows where this IP address is. And inside the container, we also want to have a route to get outside. If we want to have more than one container on our node, we have to create a bridge, and we just connect our Ethernet devices, our cables, to that bridge. You can also address it with an IP address, and after you bring it up, you can try to ping it. And in our network 42, the container number 2 should be now reachable from the host. Of course, in setups like this, you have to be very careful what you do, because if you attach a container that should not connect to another container, you're not allowed to bridge it on one common bridge. Otherwise, they can reach each other. In larger setups, this is usually separated either by separate bridges or by overlay networks or by creating automatically generated firewall rules that are assigned to a particular bridge or to a particular network interface. The other one is the user namespace. We change the capabilities for our process, but we have the same user ID mapping inside the container and outside. And as we escalate to root, we are root as well on the host. So what we really need is a local privilege escalation on the Linux kernel or the distribution. Maybe we also find a weak spot in the container engine that creates our container. Hackers, vulnerability researchers, and as well as the container engine developers themselves try to find ways how to break their own systems and containers. So they have to deal with subtle little things like if there is a file descriptor still open, can you break out, like we have seen in the proc file system example, but also how the container engine and the ecosystem works. You also have to defend against attackers injecting their own malicious images. To demonstrate this, we can have a little example here. For example, here we are the user with limited capabilities. And here in the extraction process, the attacker supplied us with a hack sudo command. And if we look into the file permissions, it is a suit binary, meaning as we run it, we substitute the user with the owner, which is root. And as we run this, we immediately change our user ID to 0, which means root. And then it's more or less game over because we have escalated to the host's root permission again. Based on that little toy example, we can imagine that's quite important to separate user IDs from host and container. And that's where the state of the art is currently heading at. Container engines try to make use of the user namespaces in order to separate the user IDs from the host. Usually that's a good thing because now you can have a root container inside and on the outside on the host you're just a normal user. But this can also bring new problems because the implementation has to make sure that all the ownerships and interdependencies to other namespaces are correct. So many of the container engines nowadays don't make use of it as a default. Using Docker, for example, you have to enable it in a JSON file or as a command parameter at startup. Okay, we have seen the moving parts of a container. We have seen the mount namespace, which is just the mount list, the list of our mount points. We have pivoted root into that, and we have been inside a separate file system. Then we restricted our access to the disk, and we used the control groups, the cgroups, for that. And then we stripped our power of our current user, which was root, to a lower privileged user. For example, user ID 1000, but we kept our capabilities, our capability to bind, for example, a network port. And as a last step, we separated our network from the host's network. We also added a route to get outside to use the internet, but we were not able to access the host. What we didn't do is to add a user namespace. So if we break out, we're still root on the machine. Is this enough? Kubernetes dropped Docker, that is true. But they only switched more or less to the same thing. Docker itself contributed to the Open Container Initiative, and they created from one monolithic part a separate part only for the container creation. And that's the runC program. So Kubernetes was changed a little bit. Previously, they used Docker and talked to Docker in order to create the containers and manage the containers. But now the kubelet talks to CRI-O to manage the containers, and this launches the runC. And this configures all the namespaces, the control groups, and the little things that are necessary to create a container. So now you know all the things to create your own program to create a container.